hasn't started the recording yet, so.
Is the recording?
Yeah, you can now introduce the speaker.
Okay. So good afternoon, everyone. Welcome to our special functions and number theory seminar for a very nice talk today by Professor Michael Schlosser from University of Vienna. Michael is a good friend of us, and I have known him since many, many years at various conferences we have been meeting. So he got his PhD at University of Vienna under the supervision of Christian Krathenthaler and Johann Sigler. And then he was at Ohio State University as a postdoc, after which he then joined the University of Vienna. He works in Q-series partitions, basic hypergeometric series, and
Lost your voice.
Can you hear me?
I can hear afterwards.
Okay, yeah.
Can't
So
hear
he
you.
works in basic hypergeometric series, partition theory, combinatorics, and many other areas. So today we are looking forward to hearing from him about bilateral identities of Rogers-Ramanujan type. Over to you, Mike.
Okay, thank you very much for the kind introduction. I hope you can understand me well. If not, then please feel free to interrupt me at any time. Also, if there's anything unclear during the talk. So I should say right away that this is not completely new, the material which I'm presenting. It's actually based on a preprint which I submitted 5 years ago, but it just recently has been accepted for publication. And to celebrate that, more or less, and Gaurav asked me to give a talk on this, so, and also to promote the subject. So, okay, I need to turn pages here. Okay. So here's the outline of my talk. So I will explain. So this is a gentle introduction to Rogers-Ramanujan identities as well. I will explain what these identities are, the classical ones. They come in a pair of identities. I will connect them to combinatorics, so to partition theory, to show their significance in some way, to indicate their significance to other areas as well, but at least on the combinatorial side, I can tell something. Then I will show you some other identities of similar type, of the Rogers-Ramanujan type. Then, since I'm interested to present you my new bilateral identities, I want to also explain how I came across them. So I need a little bit. Can you hear me well? Yeah. So I will explain a bit of the machinery of basic hypergeometric series. So I will show you some definitions, also what I mean by bilateral identities. You will see the ones I want, the Jacobi-Krüppel product identity, and then you get a feeling what it means to have bilateral extensions of identities. And then I will actually show. Then I will show you Watson's proof of the Rogers-Ramanujan identities, and that will be extended. And with help of that, you're able to prove bilateral extensions of those identities. So that will be towards the end of the talk, well, in the second part of the talk. And in the end, I will also show you some multisum extensions, if there's time. Okay. Okay, so can you hear me well still?
Yes.
Okay. Yes, okay, that's good. So here they are, the two Rogers-Ramanujan identities. As I said, they come in a pair. We take U to be either a formal parameter and consider formal power series expansions, or to let Q be a complex number in absolute value less than 1. Here you have a sum, an infinite sum, from 0 to infinity. You have quadratic powers of Q in each of the summands, and you have in the denominator the product of K factors, 1 minus K up to 1 minus K Q to the K. For those familiar with theory of partitions, it's not difficult to recognize the combinatorial interpretation, at least of this product here, and then I will explain a little bit more of that anyway. But the right-hand side, it almost looks like the generating function of partitions, but you not take all each factor 1 minus q to the n from n 1, 2, and so on. But you only take those congruent whose exponents are congruent to 1 or 4 mod 5. So that's what this is. Similarly, there's a companion identity where the only difference on the left-hand side is that instead of q to the k squared, you have q to the k squared plus k. So it's still a quadratic order in the numerator, in the exponent here. And on the right-hand side, you have a similar product, but now with the exponents n in this expansion being congruent to to 2 or 3 mod 5. So so this is beautiful in the sense that you have a sum, and it evaluates the product, the closed form. But what makes it very beautiful in addition is that you have arithmetic properties. So you have here congruence conditions mod 5 on the product side, and you don't see any reason why there should be a mod 5 behavior looking at the left on the series on the left-hand sides. So you see k squared, you see k, so you see, let's say, a product of k factors. There's nothing which indicates that you should distinguish between congruence classes mod 5, and that makes them really extremely interesting. And there are several similar identities of this type, but these were the first ones, and they were actually found by Ramanujan without proof, but then it was later shown that or discovered that actually Rogers had proved them earlier, and I will explain some of the history now. So actually, after Ramanujan passed away, 1917, I believe it was, or was it 1920? Sorry, 1920. Hardy, his collaborator, the one who invited Ramanujan to Cambridge, this eminent professor, he explained a bit of the significance of. I hear something in the background.
To pursue their aspirations and all.
Yeah.
Yeah.
They can pursue their aspiration, but
So in the sense, in the business,
I hear some voice in the background. I think it's not.
yes, do the liberty. Yes, the liberty to that. But they have free market.
Can you turn down the speaker, whoever it is? Yeah, okay, thank you. So, yes, so you can still hear me well, I hope so. Yeah, so okay, so Hardy somehow assessed some of these identities of Ramanujan, or some of the findings of Ramanujan, and especially to these two identities, he remarked that it's actually difficult to find more beautiful formula than those identities. Okay, and then he commented further that they were actually found by Rogers before Ramanujan, and there are other nice identities as well by Ramanujan, and so on. So this is one thing. So Hardy, who was very, very well known in analysis, he together with Ramanujan developed the circle method and gave asymptotic expansions for the partition function, for instance. He appreciated the beauty a lot, and over the years, so it was not just that these identities are somehow strange and curiosities, but they have been connected indeed to different areas in mathematics: the combinatorics, number theory, probability theory, statistical mechanics, representation theory, vertex algebra, knot theory, and conformal field theory, to name just a few areas. I will only indicate a little bit the combinatorial significance and number theoretical significance you've seen, which you will see soon. Okay, so here is a tribute to Rogers, who was actually the first to discover these identities already in 1894. But his identities were somewhat hidden in a long paper on page 26 in some strange notation, and this paper was essentially ignored. by the mathematical community for a long time. And then Ramanujan was actually the first, was actually the first to popularize these identities in a way, in the sense that he sent them without proof in a letter to Hardy. So actually special cases of them he was sent to Hardy. Hardy was impressed, amazed. And Ramanujan actually didn't know, was not able to provide proper proofs of these identities in the beginning. So, and that added a lot of the mystery to these identities, and also to the phenomenon of the mathematician Ramanujan. Also, the combinatorialist Percy Alexander McMahon, who published treatises on partition theory in his volumes Combinatorial Analysis, Volume 1 and 2. I guess either in the second edition of this book, or already in or at least in the second volume of the book, he published these identities without proof. Yeah, so 1917. Yeah, so okay, so Ramanujan was still in Cambridge until 1919, and then passed away unfortunately 1920. He himself found a proof of these identities. So Hardy was really strongly insisting that Ramanujan should also find proofs of his identities. So Ramanujan was able to do that. And a little bit later, that was actually funny, Ramanujan himself discovered that these identities were already published by Rogers in his paper of 1894, sorry. So Rogers was still around, but in England, not. And Ramanujan contacted him, and Rogers looked at these identities again, and he published a new proof of them. And they also it was like, I think it was more or less common work. And Rogers then found recognition in the mathematical community. And these identities are now called the Rogers-Ramanujan identities. Also, Schur discovered them independently. He gave two different proofs, one combinatorially, one analytically. But Schur was in Germany, and Germany was separated from England at that time because of the war. So that's why it was not. So that's why it was independent work. And these proofs, they were by functional equations. It was not quite clear how to come up with these functional equations without knowing the identities beforehand, or without knowing generalizations of them. But actually, a quite elementary proof, which I will use later to extend, was given by George Watson in 1929, using identities for basic hypergeometric series. So that I want to then show you then in some detail about the combinatorial interpretations. So McMahon and also Schur independently gave combinatorial interpretations, and the interpretations use notions of number partitions. As most of you are probably aware of, a number partition is a way to express n, a non-negative integer n, in parts, let's say you have L parts, number 1 plus number 2 up to number L. These all should be positive, these parts, so there are these summands, and the order should not matter, so you can order these integers in a non-increasing way. So number 1 very equal to number 2. So that is a partition. The partition function just gives the P of n would give the number of such ways to write n as a partition, to decompose n into positive integer parts. Okay, so P of 5 is 4 because there are actually P of 4 is 5, so there are 5 ways to write 4 as a sum of positive integers where the order does not matter. There are 7 partitions of 5. They are listed here explicitly. Okay, just to tell you exactly which objects we mean by partitions. And we can give actually partition theoretic interpretations of these 2 identities, but these that itself does not prove these identities. So it just shows that the left-hand side has a positive as an interpretation, the right-hand side. The combinatorial bijection is a direct one is actually still open. So it is the k square should be then written as a sum of the odd consecutive odd integers, the k square plus k, the sum of the consecutive k positive integers. So together with that, and together with the partition generating function of, well, the generating function for partitions and parts, which of size at most k, which is easily seen to be this sum here and also this product. Together with that, we can easily interpret the left-hand sides as here. And maybe I should be a little bit quicker here and just go right away to the, because I will be stuck maybe less. Okay, so there's a similar, okay, so there's a way to add the odd parts to these parts in a way so that the parts become distinct and have differences too. Yes, because if you see if you more or less, yeah, add, yeah. So these have, this has a property that the parts have distinct, differ by 2. So if you add that to a partition in a way, also in non-increasing order, you get a partition into different parts which differ at least 2. And then if you say the sum of the parts, k can be arbitrary, so you have a sum from 0 to infinity. And similarly for those partitions which start with size at least 2, as smallest part. Okay, so this is an interpretation of the left-hand side, of the 2 left-hand sides, and the right-hand sides is even easier. You have generating function of partition, the parts convert to 1 or 4 mod 5, or convert to 2 or 3 mod 5. If you've seen this before, then it's you will recognize it. If you have not seen it before, then it's anyway much too quick. My explanations here, but the idea is that to say that you have a equinumerous result. On one hand side, you have certain partitions, number of partitions n, with certain conditions, where the parts differ by at least 2. Okay, so that's the first identity. Yeah, and on the right-hand side, the parts convert to 1 or 4 mod 5. And for the second identity, a very similar equality of partitions. And interestingly, although these are easy to state, so no direct bijective proofs of these 2 interpretations are known. Here's some example, which I guess I will anyway share my slides, so you can look at them in detail if you want to. I just show that if you take n equals 10 for the first identity, you compare the partition of q to the n on both sides, you have 6, and indeed you have 6 partitions of one type and 6 partitions of the other type. And similarly, if you take the coefficient of q to the 4 for the second identity, compare them both sides, you get 4 on both sides. And you have an interpretation for this number 4 in terms of partitions. And that's the main message. Okay, so this is just to show that these identities have some interesting consequences to combinatorics, which is actually quite non-trivial because it's still open question to find a bijection. these are not isolated identities. There are other identities of a similar type. Here are the so-called Grömitz-Gordon identities, which were found much later, actually by Grömitz in his diploma thesis, actually. And Gordon had combinatorial interpretations before. And Grömitz, due to Grömitz, I believe, are these. Well, anyway, so let's not talk about the history. So the point is that you have something very similar here. Here you have k factors, but with q squared, q fourth of the q to the k. And here you have pluses instead of minuses and odd exponents instead of the even ones. And again, a quadratic power of q. On the right-hand side, you know, take again the generating function of all partitions, but you only take those exponents which are congruent to 1, 4, or 7, not 8. And here, for the second companion identity, which is almost the same, you have instead of q to the k squared, q to the k squared plus 2k here. You again have a similar product, but now where you take the exponents congruent to 3, 4, and 5 mod 8. So again, it's here actually, this is possible to prove combinatorially. So the bijections exist, as far as I'm aware. And it's also a little bit, they're considered not as deep, although they look a bit more complicated. The point is that this 8 is a power of 2. And yet the 2 you can recognize even on the sum side. So that's some kind of maybe indication that they're not as, that they could be maybe, they're easier to approach these identities. Anyway, there are also other identities now, modulo 16, for instance. So you have residue classes with mod 16, and only those parts appear in the partitions. And here we take here 8 different residue classes mod 16. Here you also take 8 different ones. And on the left-hand side, you don't see the 16 directly anywhere. So, but you see that these can be interpreted in terms of partitions as well. So this first one is due to Jackson. The other one due to Slater, who actually did a more systematic search for such identities. So the first one who searched for these other identities. So the Grömitz-Gordon identities were later. I should mention, which you've seen, 1960 and 65. Already 1947, Bailey, who is a well-known figure in basic hypergeometric and basic hypergeometric series, he initiated a systematic search for such identities. And in doing that, he actually developed what is now called the Bailey lemma, or actually the Bailey transform he did. So he didn't iterate many times, but he iterated once and twice. So he was already aware that there's some machinery which can be used and some matrix inversion underlying this machinery. But he did it very concrete to establish those identities he was interested at. And he found several other Rogers-Ramanujan type identities. And his student, Lucy Slater, she produced even a huge list of 130 such identities. And an even larger list of, I think, more than 200 identities, maybe up to 300, was then given by McLaughlin, Sills, and Simler rather recently, in the last, I'm not sure, decade or so. Okay. Now it's more or less the half of my talk. I think I'm quite okay in time. So now I'm interested in bilateral extensions of these identities. So we need a little bit of basic hypergeometric machinery. Here's some notation. A q sub infinity is just a1 minus a times 1 minus a q, 1 minus a q squared, and so on, infinite product. Again, q is less than 1 in absolute value, so this converges absolutely, this infinite product. And the finite product, a q sub k, so this is a q-shifted factorial, can be conveniently defined as this quotient of infinite products, which has the advantage that it can be defined for k being an arbitrary integer, not just a positive integer. So for k being 0, this is just the empty product, which is defined to be 1. For k being a non-negative integer, it's a product of k factors, actually the first k factors here. For k being negative, it's like a negative product, so it gives a product of missing factors, so which are then in the denominators. So that, and again, k many for k, yeah, okay. So if, yeah, or for absolute value of k many, okay. So of course, so these definitions can be, so this definition is just this quotient of infinite products here. We will often have many of these k-shifted factorials. So k is either an integer or it's infinity is on the top here. And if we have a product of n factors, we just write them as one big q-shifted factorial here, a1 up to an base q sub k. Yeah, so q is the base. I should mention that. And the word basic hypergeometric series refers to the base q, which is introduced in addition to when extending hypergeometric series to the q hypergeometric series. So you will see the definition of a basic hypergeometric series a bit later. I just want to now restate the two Rogers-Ramanujan identities conveniently now using this new notation. So here we have base q, the shift. Let's go back here. A multiplicative shift, it's by q. So you add factor q in each extra factor, 1 minus a, 1 minus a q. So a is always multiplied by q. And also remember here we had 1 minus q squared, and so on the left-hand side. And here we had jumps in 5. So we had the congruence residue classes of the exponents mod residue classes of 1 mod 5 and of 4 mod 5. So we can split this in two products with jumps of 5. So that's what we have here. Similarly here in these two other residue classes. So here with the base 5, q to the 5, and here with base q. And similar, the coordinate identities have a compact notation on the right-hand side with base q to the 8. And we have these three parameters here, which relate to the three different congruence classes we are taking the product over. And here we can conveniently write this. If you remember, still we had odd, even, and odd exponents with base q squared. Okay. Here is what the unilateral basic hypergeometric series is with r plus 1 upper parameters and r lower parameters. We have the q as one of the lower parameters, which makes the sum naturally terminate from below. And the other, A0 to AR are these upper parameters, B1 to BR are the lower parameters. In addition, with Q, we have the same number, and then we have just the argument set to the K. Okay, that's a unilateral basic hypergeometric series, a so-called R plus 1 PR series, and here we have an R psi R bilateral basic hypergeometric series. Here we leave out the Q, which was actually the reason that the series naturally terminates from below. Without the Q here, we could actually, it's natural to have infinite series in both directions, not just towards plus infinity, which we refer to unilateral, one direction. But now we have two directions, minus infinity, plus infinity. It makes sense. We also know what this, how these Q-shaped factorials are defined. That the index k is negative, that we just did on the previous slide. I should also mention that if B1 is Q, then we get the unilateral basic hypergeometric series. Of course, we have to maybe relabel the parameters, but we still have then one more upper parameter than the lower one. But here we have the same numbers. Okay, so that's maybe good to know. An example, if you haven't seen that before, but okay, this is the most important maybe identity, which let's say non-trivial identity for an infinite series. That's the non-terminating Q binomial theorem, which takes this form. It's an identity for a general 1 by 0 series, upper parameter A, base Q out of Z. Q less than 1 in absolute value and Z less than 1 in absolute value. It's very nice, and it can be used to obtain the Newton's binomial series expansion as a special case, like as in a limit, but I will not do that here because we're just looking at Q series in this talk. And this was discovered independently, more or less, by Cauchy, Gauss, and Heine in the 1840s, and Heine did then a systematic search and looked for more identities. And sometimes these Q hypergeometric series are called Heine type series for that reason. Okay, so because this is a seminar talk for a seminar based in India, and Ramanujan is the big hero, and already mentioned Ramanujan, I should definitely mention also Ramanujan's one summation, which is actually one motivation why thinking, well, we should try to extend theorems to bilateral formulas. So this Q binomial theorem, this concerns a unilateral basic hypergeometric series. There's a Q, like a hidden Q here, which is not denoted in the notation, but this is this lower parameter Q. What about going bilateral? Like if we put a B here and have a identity which is infinite in two directions. In that case, we do have an explicit evaluation. Such series are, as Laurent series, are naturally defined on an analysis. So here the correct form is that the argument set should be between 1 and B over A in absolute value. And what is very nice is that you have this explicit product containing 4 factors here in the numerator and 4 in the denominator. And okay, also if B is Q, you have a lot of simplification. And in fact, most of these factors just cancel and you're left with AZ over Z. Exactly what we have here. So this is, I find this extremely beautiful. And also actually Hardy found this in the work of Ramanujan, probably in his unpublished notes. And he published it in 1940 without proof, and described it as a remarkable formula with many parameters. It also contains, as a special case, the Jacobi triple product identity, which I will show later because we will need it. And the first proof, known proof, actually was only given by Wolfgang Hahn in 1949 using functional equations. Yeah, and now many proofs are known. for me well, and it's well studied. Okay, so you see that there's this identity, and it's possible to bilateralize it, to go actually to find something more general. Yeah. And this is maybe, okay. And so I'm interested in bilateral extensions of the Rogers-Ramanujan identities. So this is my motivation. And for this, I want to look at very close at the proof, namely at Watson's proof of the Rogers-Ramanujan identities, to bilateralize that and to more or less follow the steps, and yeah, and you'll see it will be successful. So Watson, because he wanted to prove the Rogers-Ramanujan identities, and he actually proved this, what is now called Watson's transformation, by scratch, more or less. So he proved it because he needed it for the Rogers-Ramanujan identities. So it was not that he had this was already available. What was available was the Q equals 1 case. So you replace the parameters A, B, C, D, and E by Q to the A, Q to the B, and so on. And then let Q go to 1. It's a finite identity. You can do it termwise. You get the so-called Whipple transformation, which relates to 7F6 series and 4F3 series. And this is actually relates a 8P7 series to a 4P3 series. So this is a basic hypergeometric transformation and can be proved by using the Q-Fox-Salchitz summation and polynomial argument. So I will skip the proof. I just want to tell you that the proof is available. Here it's on the slides. For reasons of time, I will skip them, but you might have a look at this. It's really not difficult. Of course, maybe it's not the most natural thing, because the point is, in order to prove this is inductive proof, and you already have to know the identity. In this case, it's maybe not so natural to, but the identity was easy to guess because Whipple had a proof. Whipple had proved the special case of it, and it was easy to find a Q in the log. Okay, so it's induction combined with a polynomial argument. Okay, now, okay, so now we start with this Watson's transformation, with this identity, which is not symmetric. That's the good thing about this identity. 8P7 is a multiple of a 4P3. You let various parameters B, C, D, and E, and N tend to infinity. You take limits. It can be, if you do it, the B, C, D, and E first, you can do it termwise because the identity is still finite. You have a rational functions identity, more or less. In the end, you let N tend to infinity. You're left with this transformation. It looks already very, you see already the number 5 appearing here. So that's a good thing. And now now there are two. So if you, without these Q-shifted factorials, you can more or less apply instances of Jacobi's triple product identity. So to get rid of this, you let A either be 1 or Q, and then you get the 2, and then you apply the Jacobi's triple product identity to the left-hand side. Actually, you have 2 terms here. You can make one term you leave as it is, the other term you identify with the negative terms in this bilateral series, in this series actually. So K, you replace K by minus K, and you can naturally extend. So this is indeed possible. This is quite nice. It's maybe like a little miracle that this works. And yes, and then you can obtain after applying the Jacobi triple product identity. You have actually here already, you see the base, you have q to the 5, k, choose 2. So you have already base q to the 5 here. And on the right-hand side, you have just base q. And for the second identity, it's similar. And this you can rewrite in the form you want and put in where you have a series with constant term 1 and similar here. It's constant term 1 anyway, but anyway, it's what it's rewritten. There's some cancellation of factors. So if you extend QQ sub infinity to Q with base Q to the 5, you can have all the residue classes and you cancel those which should be here and then you are left with the others. That's essentially what you get, or how this is obtained. Anyway, so this shows that using powerful tools like this identity of with many parameters, but it's still simple in a sense because it's a rational function identity. You can prove this identities, which here they are, the Q Rogers-Ramanujan, which are infinite series expansions without any free variable other than Q. So you cannot do functional equation, you cannot do induction. That's why they're so difficult to prove without generalizing it. Where you have extra parameters where you can do induction or function equation. Okay, now we want to apply. Okay, so the observation is that the Jacobi triple product identity, maybe let's go here, that involves quadratic powers of Q and a bilateral series. The quadratic powers of Q make it converge for k being negative and positive also. So that's good. And the Rogers-Ramanujan identities also have this quadratic power. So you can imagine that you could possibly go in the negative direction as well. So can we extend these to the bilateral series? The answer is yes. That's what my talk is about. And we can do this. Well, I also indicated that already by bilateralizing the ingredients used in Watson's proof. And maybe I explain it here. Sorry for going backwards. So this is unilateral. This goes in one direction. But we can replace n by 2n on both sides, shift the sum from k from 0 to 2n so that it goes from minus n to plus n instead. Relabel the a, b's, and c's appropriately, and then take limits. So that works. So then we do not get anything like this here, but we would have bilateral series on both sides. So this is the idea. And yeah, so instead of Watson's transformation, we have after taking limits. So this is what Bailey already obtained, is a 2 psi 2 transformation, and here we have a 6 psi 8 on the right hand side. Notice there is a quadratic power of Q already here. Yeah, and it's not symmetric, and that's also good because we want to get non-trivial identities by taking limits. And we now apply very special cases so that many of these factors disappear or cancel in different ways. And in the end, we apply the Jacobi triple product identity to the right-hand side, where we already have the quadratic powers of Q. And actually, the advantage is we don't have to combine negative and positive parts. We already have a bilateral series, so we can apply Jacobi triple product identity at once whenever we do not have these Q-shifted factorials here. Okay, so similar. Okay, so take C, D, E, and I believe F go to infinity. We okay, maybe I forgot now. Maybe we need to be a little bit careful, but I think at least C, D, and E go to infinity, and I think we're left with one free parameter. Yes, with the C or with the A, whatever. A certain. I'm just showing the results. So the first, I think there are no proofs here. Yeah, there are no proofs. The proofs are in the long paper, which you can find on my website. So here's the first result. It's a bilateral extension of the two Rogers-Ramanujan identities. So we have the one identity and the companion identity. On the right-hand side, we have product with two terms. Why we have two terms? Because we have two terms here. We have the one and then the minus another one. So for the one, so suppose we don't have these two shifted integrals, we can apply the Jacobi-Triple product, and then we have a second term. Typically, it's like that. Yeah, and we have a free parameter Z. So it's a yes, and it's again as a Q-series expansion. This for Q less than one, it converges absolutely everywhere. We should take Z not being 0 or infinity, of course. Like you will do this on the complex plane. The 0 is here a pole, and you can recognize maybe theta functions here implicitly. And of course, there's some kind of symmetries involved, which I maybe cannot explain now so much, but it's connected to the Jacobi triple product identity, which is applied. Also, you have the base q to the 5 visibly here on the right-hand side. So this is similar. You already see q to the 3, q2, q2, 3. It's like kind of symmetric. Here you have q to the 4, q to the 1, 1 and 4. You see? And if we take z goes to 1, we get then these two terms combine. There's a number. We have to cancel some of the first factors in this quotient here. But then we can. It's easy to see that we cover the classical Rogers-Ramanujan identities. But what is also possible is the following: we can replace q by q to the 5 and then specialize z. So the point is, maybe I explain it here. So we can specialize z such that one of these two terms cancels, so that is 0. So for instance, if z to the minus 5 would be q to the 3. With other words, if you replace q by q to the 5th, you would have q to the 15 here. And if then you let z being q to the 3rd, this will create this a 1 here, and a 1 in the infinite product, which makes it vanish. So this will just drop out. So with these specializations, which I'm pointing out on the next slide, one of these two infinite products cancels, will just be 0, and you have really a product formula. And these are what I call now bilateral companions of the classical Rogers-Ramanujan identities. So you have now base q to the 25, because we have base q to the 5, and then replaced again q by q to the 5. But on the left-hand side, we have base q to the 5. And because q, we have here q squared, q third, q fourth here, and not q to the 5th, these series naturally do not terminate from below, but they really go infinitely in both directions. And again, we have quadratic powers of q here, which make the series converge. So I find these quite beautiful. You see also different combinations, q 2, 3, 1, 4, 1, 4, 2, 3, appearing in these products on the right-hand side. Okay, and these can be compared to this pair. So now we have 4. It's also because the residue classes congruent to 5 are 1, which are not zero, are 1, 2, 3, and 4 that appear here. Why we have exactly these quadratic powers of q, maybe that's not quite clear here, but they're chosen so that it makes the right-hand sides factorize. Okay. Similarly, we can do it with the Gremlin-Gordon identities. We're getting these identities now with the extra parameter z, like a formal Laurent series parameter z. And again, if z goes to 1, we recover the classical Gremlin-Gordon identities. In that case, we have to take a certain limit here because z appears here as a z equals 1 would be 0, but it's also a pole, so we can cancel that, and also here. But then these two are actually the same, and yeah, well, anyway, so there's some simplification. But also, if we replace q by q to the 8, and then replace z by different powers of q, now z being q to the 3rd, q to the 5, or q to the 7, again, coprime exponents which are coprime to 8, 1, 3, 5, and 8, 7. Before we have 1, 2, 3, 4 with base q to the 5. Now we have base q to the 8. So we get again a set now of 4 identities. With those specializations, the right-hand sides simplify because one of these terms will drop out. Again, I find this beautiful. And yeah, okay. Maybe I just continue. There are other identities obtained by this idea of getting rid of these Q-shifted factorials in this Bailey 2 psi 2 6 psi 8 transformation. And like in the 6 psi 8, we want to cancel these shifted factorials. That can be done in different ways. Here is one companion. It's not a companion, it's one bilateral identity where with base q in the numerator, base q squared in the denominator. Interestingly, with base q third here on the right hand side. So it's also quite non-trivial. It's maybe a little bit similar to the quintuple product identity or something like that. We can imagine you've seen that before. Here we have base q squared, with the base q squared, and q to the 6th. Yeah, and other identities. And we can specialize the z. So here we don't need to specialize z because we already have a product. Here you might say this is not really a product formula because we have 2 terms. So if you just want to have 1 term, you can specialize z so that this simplifies. And we get additional identities. They're here with mod q to the 6th, 16, 32, yeah. And of course, these have all been checked on the computer as power series extension in Q, where we split the sum in k greater equal to 0 and k negative, and the usual Taylor series extension. Okay, I think my time is over. I just wanted to maybe briefly show that just a few more slides that there are multi-sum extensions as well of the Rogers-Ramanujan identities and of the Gremlin-Gordon identities that were discovered by Andrews in analytic form, by Gordon and Comatro form. And this is due to Andrews. There's also Bressoud's even modulus analog of Andrews-Gordon identities. For R equals 1, or actually 2, sorry, the trivial case, it's just a special case of the binomial theorem. It's like the Q exponential expansion. So that's why this is nothing new for in 1 dimension, but for a multi-sum, these are interesting. And they can be proved by the Bailey lemma with the Jacobi triple product identity. And also this works in multi-time. Also, one can multilateralize these identities so that on the bottom, you do not have a Q. Let's say the Q square makes this terminate naturally from below. And here you have a Q here, and here you have a Q square. You can more or less think of replacing that Q by ZQ or ZQ square, and you can naturally go in two directions. And remarkably, on the right-hand side, you still have just two terms and not R plus two terms, R plus one terms, or I don't know what. So it's not dependent on the number of summation indices you have. And of course, you can also do the trick that you specialize that in different ways to get rid of one of these terms. So yes, so in this case, for the Bristwood identities bilateral extension, the right-hand side is just closed form, it remains. Yeah, okay, and I'm not giving you the special cases now because they look very similar to these identities here, and they're just huge sums, and you can mention that it works, and you can see the details in my paper, which is with the same title of my talk on my homepage and on the archive. So thank you very much for your attention.
Thanks, Michael, for a nice talk. Are there any questions?
Hi, Michael. May I ask a question, please?
Yes.
Yeah, thanks for the very nice talk. I wanted to ask about the bilateral Rogers-Ramanujan identities with the Z.
Yes.
Would that allow enough freedom to give a direct proof by functional equations? So that's the first question.
Yes, yes. So I come across these identities by using bilateral by basic hypergeometric series. But once you have these identities, for instance, maybe I just show you the first one, this one, yeah. You can prove them by functional equations, and you can use both sides as elliptic functions more or less. So the theta functions appear. So you can, I think you have to renormalize the, you multiply both sides with something, and then you see that it's more or less elliptic. I think this product here you put on the other side, and then you can shift set by or you can also maybe multiply q by q squared first, and then you shift set by q, and you see a certain functional equation appearing here. And it can be used to prove both sides. Yeah, and that has been also, that actually has been pointed out to me by a referee in my paper, and I included the details in my paper. I still think that it's like a verification proof, because what is actually used then, we still need to prove a special case, like Z being one constant, let's say Z being one. So you still need the Rogers-Ramanujan identities, the classical, to prove it. Yeah. In this method. Because you have a functional equation, you iterate it, and then you need like a special solution. Like Z equals 0 does not work, but you need something, and that will be Z equals 1 in this case. Yeah.
Oh, that spoils it a little, doesn't it? Because the idea
spoils it a bit, because you need the so you need the unilateral identities, and then you can prove you need one special. You need it at some point. You want to show that both sides of something are a constant, and that you put let them Z goes to 1, and you know what somehow the q to the 5 has to come into play as well. And that's by computing this constant. Yeah.
Do these identities have combinatorial interpretations?
Yes, so I also in the first version of my paper on the archive, I gave a list of combinatorial interpretations for the two, not of this, but of these identities. So I interpreted, actually, I rewrote this in as two series, k greater equal to 0 and k lesser equal to -1. And one can give combinatorial interpretations of both sides. The referee said this is not very interesting because it's very complicated. The formulations take a full page of so it's like multi-partitions or vector partitions. You have many, you have many products, and you can, so it's in principle, you can imagine you have an interpretation on both sides, but yeah. Of course, it does not help now to, yeah. Maybe what you're more interested in, may I say, add something? Tim Hooper has pointed out to me that there's a connection to modular forms of these left-hand sides. So these are like modular forms of weight 1/5 or so. These appear somehow as, I don't know, as generators of some group or what. Yeah. You can, I also added a remark in my paper, so you can take a look at that. So it's not really my area, but it was just to maybe to give some evidence that these, because the Rogers-Ramanujan identities, they are connected to representation theory, to modular forms, let's say, in different areas. Of course, one could ask, what about these identities? And there's some hints, yeah, that this can be done. Of course, to make it, maybe one has to renormalize. Maybe this factor here, for instance, q to the 4 should be put on the other side first, and then the right-hand side will be completely positive, yeah, q positive. That you maybe want for a combinatorial interpretation, yeah, and so on. So I just decided to put the products all on one side. Yeah, but for certain interpretations, it might be good to rewrite this.
Great, thank you.
You're welcome.
Any other question? Okay, if not, then I'll request everyone to unmute themselves and clap for Michael for the